Okay, so what we're really looking at here is similar to what we did yesterday. Okay, we're going to have an inclined plane, because that's essentially what the rock is rolling down. Okay, so the rock starts up here, 400 kilograms. When it gets down to here, okay, it's still 400 kilograms, but it's moving at 4.5 meters per second. Okay, and obviously the length of the ramp is 30 meters. Force of friction is 800 newtons. Okay, what we're looking for is how high it was dropped from. Okay, this one's actually a bit easier than the ones we did yesterday because there's less numbers here. All right, so we give you a few minutes, see how you do on that. So, with this question, a couple things we have to realize in order to get it started. Is work being done? Yes. Friction is acting on the ball, on the rock, as it rolls down the ramp. So it's going to have more or less energy at the bottom than it had at the top. Less. Friction takes energy away. Okay? So we definitely know that this is a work energy theorem question because there's a change in mechanical energy due to the friction acting on the rock. Okay, now that we've established that, now we need to look at some of the values that we have or that we are looking for. It says the rock is dropped. If the rock is dropped, how fast is it moving initially? Zero. Okay, so I know then that VI is 0 meters per second, which means it has no kinetic energy initially, only potential. Okay, the end of the question is talking about its lowest point. At its lowest point, I know that it's moving at 4.5 meters per second, but that's also its lowest point where the height would be 0. Okay, am I doing that thing again where I talk myself through a question? Okay, I don't just do that because it's a way to teach you. I do it because it's the only way I know how to do a question. I have to talk myself through it. Okay, so now that I've established those things, now I can go back to my work energy theorem idea here, and I can say that the work being done is going to be the final potential plus the final kinetic minus the initial potential plus the initial kinetic. And I've already established that this one is 0 because it was being dropped, and that this one is 0 because we're dealing with the bottom of the ramp. Everybody okay with that? Okay, so then I'm going to expand this formula out now. The work being done against friction will be the force of friction times the length of the ramp, or D, and that's going to equal 1/2 mvf squared minus m times g times h initial. Because I only have initial potential, I only have final kinetic. So I have a lot less numbers in this one than I had in some of the ones I had yesterday. Now, what is the question asking me to find? Height initial. All right, so if I want to find height initial, this is being subtracted here. What should I do with this thing? Yeah, I'm going to bring it over here to make it positive. All right, so I'm going to have m times g times h initial plus force of friction times distance equals 1/2 mvf squared. And then I'm going to bring this over by subtracting it, right? Okay, so here's why this should make sense from a logical perspective. My initial energy should equal my final energy minus the work. Okay, minus the change in energy. Final minus the change should give me what I started with. Everybody okay with that idea? Okay, now, this work, is it positive or negative? It's negative. The friction is taking the energy away. The force of friction is a negative value. So I'm actually going to be subtracting a negative, which means I'm going to be adding. Is that okay? It should be, because what did we say about the initial energy and the final energy? One of them was bigger. Which one? The initial. Okay? I'm losing energy to friction on the way down. This number should be bigger. All right. So when I punch in my numbers, gosh, sorry, I'm not done manipulating it. I still have to get HI by itself. So what do I do with M and G? Okay, so now my initial height will be 1/2 times 400 kilograms, the mass of the rock, times 4.5 squared, that was the speed of the rock at the bottom, minus the force of friction, which was 800 newtons, times, it's what, 30 meters, right? Okay, so there's the length of the ramp, and then I'm going to divide that by 400 kilograms times 9.81. Right, so that should give me my initial height of the rock. 0.5 times 400 times 4.5 squared, okay, minus 800 times 30. Actually, negative 800. Stupid. Okay, and then divide that by 400 times 9.81. Okay, so the rock is initially 7.1 meters above the bottom of that track that it's on, or tunnel that it rolled through, whatever.
I had a question to help Mr. Batchek. With the calculator, he doesn't want to go up. He just push up. This is nothing to do with physics.
Yeah, you know what? My emulator won't let me do that. I can't go up either.
So how do you go up?
I can't.
Would there go back to fix the answer?
Oh, I just put in a second entry. As long as it was the last entry, then I can go back in it. But as soon as I hit enter, it won't let me go up or grab anything.
I thought because you were doing that and he couldn't do it, so I was wondering what you were doing.
Oh, I could do it here because I hadn't hit enter yet.
Oh, okay.
Right? I hadn't hit enter, so I was still able to go back in what I was doing. But yeah, I don't know why, but they can't, these ones can't be. Should get a better emulator. But. Okay, so does that one make sense to everybody? That used to be an exam question. Okay, so one like that. Okay, and the reason I had that one on the exam and not one of the ones from yesterday was it's a bit shorter. Right? It only had potential at the beginning and kinetic at the end. There weren't as many numbers in there, so it doesn't take quite as long to figure it out. Okay. That's not the one either. There's the other one. Okay, I want you guys to try this one, okay? Read it carefully. The constant velocity part is important. Actually makes the question a lot easier, okay? Because it's moving at a constant velocity. All right, I'll give you guys a few minutes on that one. All right, so when starting this problem, how many people went about this finding F parallel and looking at the length of the ramp? Okay. How many people ended up doing it using just work energy theorem? Okay, so if we solve this just using work energy theorem, the key point here is that it's pushed at a constant velocity. There's no change in what kind of energy? Kinetic. The only change here is the potential energy from the bottom of the ramp to the top of the ramp. So if I want to calculate the amount of work done, okay, it's just going to be the change in the potential energy, which for this question is m times g times h, so that is 80 kilograms times 9.81 times 7 meters. And we're 5.5 times 10 to the 3 joules. How long does that take? Super quick, right? It's one calculation, and I don't even have to manipulate to do it. It's just plugging in numbers. But if I do this using forces, I can still get that answer, but I have to calculate the angle using the hypotenuse and the opposite side. I need to put a box on here that's 80 kilograms. I need to find FG. I need to find F parallel. And then I have to understand that the applied force is equal to F parallel because it's moving at a constant velocity. Okay? And then I would multiply F applied by the distance by 10 meters, and I would still get this number. But that's a lot more work. Way more work. Okay? And I'm not saying it's not going to get you the right answer. It is, and it's a perfectly valid way to do it. But it's a lot more work. Okay? And I'm all about making your lives simpler and saving you time. Okay? So the work energy theorem is definitely going to be quicker on a question like this. Okay. Okay, this one I want you to try because I'm going to relate it to a real world example or a real world situation here after you're done doing it. Okay, so you have a car that's 1,165 kilograms traveling at 55 kilometers per hour. What do you need to do with that number? Convert it to meters per second. Okay, it's brought to a stop while skidding 38 meters. I want you to calculate the work done on the car by frictional forces. Because it's force of friction that stops you. When you slam on your brakes, friction steals all your energy. That's how you stop. Okay? Give you a couple minutes on that. Okay, so once again, there's two ways to do this. Right? This can be a work energy theorem question where what kind of energy is changing? Kinetic. Yeah, I'm slowing this thing down. It doesn't mention anything about going uphill or downhill or falling. Okay, so there's no change in potential energy here, but it's definitely changing its velocity, which means it's definitely changing its kinetic energy. So VI is going to be 55 kilometers per hour, but we have to convert that to meters per second. So 55 divided by 3.6, and it gives me my meters per second, so 15.277. Okay, meters per second. What's my final velocity? 0. Okay. Work is a change in mechanical energy. In this case, I'm only changing the kinetic energy, so I only need to write that. All right, so that's going to be 1/2 mvf squared minus 1/2 mvi squared. And what's this? 0. All right, so basically I'm just going to have negative whatever 1/2 mvi is. Okay, so 0.5 times the mass of the car, which was 1,165, and times our answer there, 15.277 squared. Okay, so there's how much work is being done by the car in order to stop it, by the brakes. Do brakes get pretty hot? Okay, if they lock, then the tires get pretty hot. Anyone ever seen when a car looks like when the tires lock up on dry pavement? Smoke just pours out of them. Okay, they literally incinerate, okay, as they slide along the ground. Okay, so there's a lot of work being done because the car is big and heavy and moving pretty fast. There's a lot of work to be done there. Okay. Now, if I'm looking at this from a forces perspective, okay, I don't even think I can solve this using forces. I don't think there's enough information. Mass, I can calculate acceleration. Yeah, I could do this with forces. The only force acting is friction, so I can calculate it because it's the net force. And then I could go net force times distance and get that. But that's 2 or 3 calculations, where this was 1 calculation.
How did you get the meters per second?
I divided by 3.6.
Why did you do that?
Because that's how you do it. Better answer is, if I'm doing a compound conversion, and I have kilometers per hour, okay, I want to get that to meters per second, I have to multiply by 1,000 to get the kilometers to cancel off. And then I have to say that in 1 hour, there are 3,600 seconds. So my hours cancel. So basically, I'm taking whatever I have in kilometers per hour, multiplying by 1,000, and then dividing by 3,600, which is the same as saying divide by 3.6. Yeah? All right. Now, looking at this example here, this example is really important because it takes a lot of energy to stop a moving vehicle. Vehicles are heavy and they can move really fast. Okay? Children don't always recognize that. Children aren't too bright when it comes to crossing streets. Okay? If a child runs out in front of you and you have to slam on the brakes, okay, you are relying on physics to take care of all of your energy and turn it into something that will not do work. on the child in the street. Okay? Makes a big difference. But here's the problem. Speed has an exponential relationship with your stopping distance. Okay? What we have to look at here is this. If I am relying on the force of friction to stop me, I am hoping that the work friction does will be obviously the change in my kinetic energy. We're okay with that idea? That's what we just did, right? Force of friction. Well, we didn't have the force of friction part, but that's the work equals the kinetic energy that I start with. Because at the end, I want to have no kinetic energy. I'm all right with that. Okay. So VI is squared here. Agreed? So if I want to figure out how far it's going to take me to stop, I'm looking for D. Yes? Okay, so what would I do with FF if I want to get D by itself?
Just
Divide over the other side. Okay. I only have one thing in this formula that's squared, and it's V. So as V gets bigger, its effect on D is exponential. If this is, let's say, 2, okay, let's say it starts out as 1, okay, it starts out as 1, I'm going to calculate this D. But if I double it to 2, it's not 2, it's 2 squared, which is 4, okay? So if I double my speed, it's going to take me how much further to stop? 4 times as much distance to stop. So if you're going 60 through a 30 zone for some reason, it will take you 4 times the distance it would take you to stop at 30. Okay? If you doubt me, I'm going to prove it. Right? Prove it to you right here. We're going to take some numbers. We'll take the numbers from this thing here. We're going to say the mass of the car is 1,165 kilograms. And let's say we're going the speed limit. Okay, so let's say we're going 30 kilometers per hour. Okay, so we're going, that's 8.3 meters per second. Okay, so at the speed limit, if I want to calculate how far it will take me to stop, I'm going to need the mass and I'm going to need the force of friction. Okay, typical car, 1,165 kilograms, force of friction that's stopping the car is going to be somewhere around probably 8,000 newtons. Okay, that's how much friction there could be to stop your car. All right, so if I want to plug these numbers in and solve for D, for someone going the speed limit through a playground zone or a school zone or a construction zone, okay, it's going to be 1/2 times the mass of the car, 1,165, times 8.3 meters per second, but that's got to be squared in the formula, and then divide that by the force of friction, 8,000 newtons. Okay, so 0.5 times 1,165 times our answer squared, okay, divided by 8,000. All right, so at that speed, it'll take 5.05 meters for my car to stop. Okay, that's at the speed limit. Okay, 5.05 meters, guys. So from here, that's not too bad. You get a pretty good chance of stopping before you hit the kid. Okay, 5.05 meters. Okay, not too bad. Now, how many of us actually go 30? Yeah, me. I have kids. I go 30. I fully admit to that. Yeah, I have kids. I go 30. Okay, but you know what we always do it, and you know what? I'll admit that I do it out there in that construction zone that nobody's working in. It's still 30, even though there's nobody there. Okay, I go 40. Right, I justify that to myself. 10 kilometers per hour is not that big a deal. It's not that much. It is. It's a big deal. Okay? I'm only going 10 kilometers an hour faster than I'm supposed to go, but watch what happens to my stopping distance. Okay? So if I change this now, instead of having it be 30 to 40, All right, so 11.1. So now I do this same formula, same car, 1,165 kilograms, okay? But now it's times 11.1 squared. Same car, so same braking force, 8,000 newtons. Watch what happens to my stopping distance. Okay, so I'm going to have 0.5 times 1,165 times my answer squared, okay, divided by 8,000. It's 9 meters now. Okay, it nearly doubles. Very nearly doubles. And I only went 10 kilometers an hour faster. Okay, I went like 30% faster. But I nearly double my stopping distance. Is that a big deal? Okay, because 9 meters is longer than this room. Okay, before the stopping distance was from there to there. That was kind of acceptable. Now it's almost twice that. Okay, that's the difference between me having dinner with my children or planning their funeral. I know that probably seems pretty harsh, but that's the reality of it. Okay, that 10 kilometers an hour nearly doubles your stopping distance. That's a lot. Okay. The other part of it is, even if that 5 meters wasn't enough, do I slow my car down a lot in that 5 meters? Even if, unfortunately, I hit the kid here, okay, how fast am I moving? Not very fast. I might, maybe they get a bruise or something like that, but nobody's hurt real bad, okay? If I'm going 40 when I hit them here, I'm going to still hurt them really bad, maybe even bad enough to kill them, because I've got a lot more energy still in my car because I had a lot more to begin with. Okay? That's what you got to think about when you're saying to yourself, that 10 kilometers an hour is going to make all the difference in the world to me. That's going to be the difference between getting to school before the bell. Well, get up earlier then. Okay? Because it's not going to make the difference. Here's why. That 10 kilometers an hour over the length of this playground zone or school zone is going to make about 8 seconds difference in your arrival time here. Okay? It really doesn't make any difference. You're better off to go that speed limit. Okay? And here's the other part of it. This all assumes that you react instantly, which you can only do if you're paying attention. Okay? I hate to say it, but man, there are a lot of drivers out there who are not paying attention. I drove beside a lady this morning who was doing her makeup. Okay? Yeah. And I've seen worse. I saw a guy reading a newspaper once. And it wasn't a stoplight. He was driving. The newspaper up on the steering wheel. Like, folded like this, driving. Okay? Okay? And that's not even including the phone. I mean, the phone is the worst thing. Okay? Like, people just don't see anything when they've got that phone out in front of them while they're driving. Okay? My wife was telling me a couple years ago, out in front of Westmount School, there was one of the sheriffs was running a speed trap, and he nearly got killed because there was a lady. My wife was parked on the side of the road, and she saw it happen. Lady on her phone through the school zone at 60, like roasting through the school zone, at least 60. I mean, this is my wife's estimate. Okay, like at least 60 on her phone. Police officer steps out to stop her. She doesn't see him because too into this. Nearly runs him down. He has to jump out of the way. In front of a school on a school day when the kids were getting out. So like 3:30. I mean, I would imagine I would hope she lost her license. I mean, that's just, you should never drive again because you're just too stupid for a license. Okay, if you're going to do something like that. Double the speed limit through a school zone when kids are crossing the street, and a cop steps out in front of you and you can't see him because you're too into whatever's going on your phone. Okay, please guys, when you're driving, for God's sake, put the phone away. Okay, put it away. It's the worst thing to happen to driving skills ever. And people just don't pay attention anymore. There's people that watch TV shows, they put their phone on the dash in front of the speedometer and all the other gauges they need to see, and they drive and they watch TV. Okay? They watch something streaming on it. It just boggles my mind. Okay? Don't be one of those people. You'll eventually hurt somebody. Okay? So don't do it. And remember this, speed is exponentially related to stopping distance because of physics, because of work energy theorem. Okay? Keep that in mind. That's why we have special speed limits for special places. Construction zones, playground zones, and school zones. Okay? Because speed is exponentially related to stopping distance. You may, after all that. Yeah. All right. I'm going to give you guys, actually, I'll give you a little break here, and then I'm going to go into just some more stuff about kinetic and potential energy in preparation for the lab we're going to do tomorrow on energy conversions. Okay, so I'll give you a couple minutes here. So just want to quickly review here kinetic and potential energy, and then talk a bit about the situation that we're going to have tomorrow when we're doing our energy conversion lab. Okay. So in our energy conversion lab tomorrow, we're going to be converting potential energy into kinetic. Right? We're going to be looking at a very simple situation, cart rolling down the ramp. Okay? In a perfect physical world, all the potential energy at the top of the ramp should be converted into kinetic at the bottom. Okay? Obviously, in tomorrow's case, that's not going to happen. There are going to be things in there that are going to cause the energies to not be equal. Okay? We're going to have a look at just how inefficient that conversion of energy is. Okay? It's actually incredibly, surprisingly inefficient, okay, converting two very simple forms of energy into one another. All right, so gravitational potential energy. You have it because of what? Because of gravity. Well, gravity is present right now, but I don't have any potential energy. Height, yes. And what else? There's actually three things. Mass, yeah. You can't have energy if you don't have mass. Something without mass can't do any work. Okay, so you have to have mass, there has to be a gravitational attraction, and there has to be height. You have to be able to fall. Okay, that's what gravitational potential energy is dependent on. Those three conditions are met, and there's gravitational potential energy. Question? Nope? Okay. All right, so that's why some of these amusement park rides are designed the way they are. Okay, back when we used to go to West Edmonton Mall for our trip that now we can't do anymore, okay, one of the rides is the space shot, where you are shot up into the air and then dropped back down. Okay, it's exciting because, well, when you get up to the top, you have a lot of potential energy, and you feel like you're falling all the way back down to the bottom. It gets converted into kinetic. Okay, and lots of rides depend on that. Roller coasters depend on that as well. Okay, on the Mindbender, you're towed all the way to the top of the track, and then you just roll. Okay, down the track, and you convert that potential energy from being way up high into kinetic energy at the lowest point. Okay, it converts very quickly, and you can get going very, very fast. All right, so this formula that we've dealt with before, m times g times h, calculates potential energy. But really, all it is this formula. Force times distance. What force are we talking about? Yeah, gravitational force. Okay, and we calculate the force of gravity by going m times g. And since gravity works vertically, okay, a height is a vertical distance. So really, this is just saying force times distance. That's where we get that from. Anytime you're changing something's gravitational potential energy or working against the force of gravity over a vertical distance. Okay, we don't even need to do that one because it's too straightforward. Same with that one. Okay, so if we have a pile driver, anyone know what a pile driver is besides the wrestling move? The wrestling move actually does a very good impression of a real pile driver. Okay, a real pile driver is just a big hammer. Okay, you take a weight up really, really high, you give it a lot of potential energy, and then you drop it on top of the piling. Okay, and when it hits the piling, it drives it into the ground, hence pile driver. Okay, the wrestling move looks very similar. Okay, you drop somebody on their head. Okay, all right. So obviously, all a pile driver is doing is converting gravitational potential energy into kinetic energy, and then the kinetic energy can do work. Can potential energy do work? Nope. It has the potential to do work, but in and of itself, potential energy does not do work. Okay? It has to be converted into something else, usually kinetic energy, in order to do that work. It's got to be moving in order to do work. All right, we're going to skip those because we've talked about that kind of stuff. Now, with kinetic energy, you have kinetic energy if two conditions are met. You have mass and speed. You're moving. Okay? To any extent, as long as you're moving, you have some kinetic energy, right? And we just talked about how that movement, that speed, has an exponential relationship with the amount of energy you have. Okay? An object going twice as fast as another object of equal mass has 4 times the amount of energy as that other one. Okay? If something is moving 3 times faster, it has 9 times the amount of kinetic energy as an object moving 1/3 that fast. Okay? So there's that exponential relationship between speed and kinetic energy. All right. Let's have a look at this one. This is a quick one. Okay, so on a highway, we have a car with a mass of 1,200 kilograms, okay, traveling at 20 meters per second. It has kinetic energy equal to a loaded van that has 4 times as much mass. We're looking for the speed of the van here. Okay, so the van is 4 times heavier, but it has the same kinetic energy. So can we basically say then that the kinetic energy of the car is equal to the kinetic energy of the van? Okay, so we can say then that 1/2 times the mass of the car times the speed of the car squared equals 1/2 times the mass of the van times the speed of the van squared. Okay, how do I get the speed of the van? Right. And I square root, and now I've got the speed of the van isolated. Okay, so that's going to mean 0.5 times 1,200. Whoop, it's got to be on. 0.5 times 1,200 times 20 squared divided by 0.5 times 4,800, which needs to be in brackets. And then I gotta square root that. Okay. Van's 4 times as heavy and is moving half as fast. Okay. Again, that's that whole exponential relationship, okay, between speed and kinetic energy. Okay? This thing has way more mass. It has to go a lot slower. Not 4 times slower. Okay? Half as slow. Okay. Skip that here. Number 2. All right, let's talk about the lab for tomorrow here. Let's just go straight to that. Okay, so tomorrow, this is going to be our situation. Okay, we'll have our cart at the top of the ramp, starting from rest. Okay, so we'll have VI equals 0 meters per second. Okay, and we'll know the height of our ramp, whatever you're going to decide to build it to be. Okay. And then we'll have our cart at the bottom. Now, we'll use the carts that we had there that can tell us how fast the cart is moving at the bottom of the ramp. Okay, so we'll be able to get those speeds, and we'll be able to compare the two. Now, we'll have VF here. It'll be, well, we'll know what it is. And what's our final height going to be? Right. Okay, so we're going to compare those two things. Theoretically, that should be true. Agreed? But it's not going to be. Because of what? Yeah, because of friction. So then, if we know they're not equal, then we know that's the situation we're going to be dealing with tomorrow. Some work is going to be done against the force of friction along the length of the ramp. Well, we know the length of the ramp. Yeah, because we'll be able to measure it. Okay. Will we be able to calculate the force of friction? sure hope so. Okay? We should be able to calculate it. We should know everything else. One of the other things we're going to be looking at is this. Efficiency. Okay? You talk about this in Science 10, but like it's just a brief concept. Okay? Efficiency is your final energy, essentially, okay, divided by your initial energy. Okay? If something is perfect, its efficiency will be 100%. Okay? That number will come out to 1. Nothing's 100% efficient, so we have to see tomorrow how efficient that conversion is going to be. Okay. So, you know, if we do a pretty good job of everything and everything works pretty well, maybe it comes out to like 0.75, which would be 75% efficient. Maybe it comes out to 30, who knows? Okay, but that's one of the things we're going to be looking at tomorrow. One of the things you're going to be asked to calculate, okay, will be the efficiency of that energy conversion. Right? So you'll be looking at all of those variables. Those are all things you're going to have to measure. Okay, make sure you have recorded, because oftentimes with this lab, I have people set the lab up, run the whole lab, and then realize after the fact that they didn't measure something really important. Okay, really important measured values are going to be the height of your ramp, without which you will not be able to calculate your initial energy. Okay, your final speed, which the cart's sensors will provide to you, and okay, obviously the mass of your cart. Make sure you record that off of the cart itself, because we wrote it on all of them. Okay, and obviously then the length of your ramp. Okay, that's another one. The length of the ramp will also be an important number, because you need to know the distance over which friction is going to act in this. It doesn't take long to do the data acquisition for this lab, and so you should have a fair amount of class time tomorrow to work on the lab report, make the analysis and stuff like that done. Okay? Especially now that I've explained part of it today, okay? You'll have less of it to do tomorrow. All right, questions on how that's going to work for tomorrow? I want you guys to try question number 3. Okay, that's Meteor Crater in Arizona. Okay, it's a real place on Earth. I want you guys to see if you can calculate the kinetic energy of the meteor at the instant of impact. Okay, remember that they're giving you speeds there in kilometers per hour that you will need to have in meters per second. Okay, and then they talk to you about this whole tons of TNT thing, which is how we measure the explosive yield of stuff. Okay, so see if you can figure that one out. We'll give you a couple minutes on that one. Okay, well, let's have a look at this one. So they want us to calculate the kinetic energy of the meteor. That's a pretty simple calculation. All we have to do is plug it in to this formula, 1/2 mv squared. The biggest thing is converting the kilometers per hour to meters per second. Okay, so we're going to have 1/2 times the mass, which is 2.6 times 10 to the 8 kilograms. Okay, and then times our speed in meters per second. So it was 7.72,000. Divided by 3.6, okay, should give me 20,000 meters per second. And that has to be squared, okay? So 0.5 times 2.6 to the 8, okay, times 20,000 squared. All right, so this thing has 5.2 times 10 to the 16 joules worth of kinetic energy when it strikes the Earth. Okay. Now, in the second part, they're telling us that 1 ton of TNT explodes. It releases 4.6 times 10 to the 9 joules worth of energy. Okay. In terms of tons of TNT, how much energy did the meteor have upon impact? What do I do with this number and the one I just calculated? Divide them, yeah, exactly. If I divide the number I just got by this 4.6 times 10 to the 9, okay, then we're looking at 11,304,347 tons of TNT. That is 11.3 megatons of TNT. That would be the equivalent of some of the largest nuclear weapons we have. Okay? To give you an idea, the bomb dropped in Hiroshima was 1 kiloton of TNT. So it was the equivalent of 1,000 tons of TNT. Most of our nuclear weapons are now measured in the megaton range, which would mean you do a Minecraft thing, you pile like 1 million tons of TNT in one place and blow it all up at the same time. Okay? So 1 megaton would be 1 million tons of dynamite packed in one place and blown up at the same time. Okay? This is 11 million tons, which is why there's a big hole in the earth where that thing hit. Okay? It's kind of a big deal when something like that happens. It's a lot of energy. Okay? All right, making sense? Everybody's good with that one? Okay. That's too easy. Okay, when you look at this question, does it sound like there's a fair amount of work involved in it? It talks about pushing this thing up the incline, okay? It tells you the force that's used to push it up the incline, okay? And asks you to calculate the potential energy when it's at the top. How many calculations do I have to do to get that? 1. Okay. Most of the information in that question is irrelevant. Okay? I can just solve this by calculating the potential energy of the box when it's at the top of the ramp. It doesn't matter how it gets there. It doesn't matter whether I lift it to the top, drag it up, push it up. It has the same amount of energy when it gets to the top because it's the same distance from the center of the earth. Okay, the same distance off the ground. Okay, it's important to remember that. That's the whole reason that we build ramps. Ramps make work easier. They don't make less work. Okay? Yes, to push this thing up the ramp would require less force than it would to lift it to the top. Okay? That's the whole purpose of a ramp, is to make work easier. Okay? But in the end, when it gets up here, it has the same amount of energy regardless of how you get it there. I almost always have a multiple choice question about that on your unit exam. Okay? It's important to remember, okay, that a ramp serves one purpose: make work easier, not make less work. To get something to the top of a ramp requires the same amount of work, no matter how it gets there, because it's about the change in energy between the bottom of the ramp and the top. Okay? All right, get your desks wiped off and get ready for lunch.